Hi, my name is Ernest James. I am a senior computer science student studying at the University of Mississippi. We are designing a UAV that will autonomously launch and scout the field and communicate the location of a destination to a UGV, then precisely land on that UGV, all in an area without GPS. We solved this by bringing together an interdisciplinary team of electrical engineering, computer engineering, mechanical engineering, and computer science students. We worked collaboratively using Jira, GroupMe, and in-person meetings. And after researching the cutting-edge drone technology and simulating the challenges, we decided to incorporate the most applicable aspects of each into our final design.
This is our drone. It's a 500mm four-rotor design with a 3D printed hood to protect the electronics inside. We're using a Here 4 as our main sensor hub because it has multiple related sensors in a weight-efficient package, and it communicates to the rest of our system in a cost-effective manner. We're using a Pi 5 because it has more memory than the Jetson Nano at the same price, and it interfaces with multiple devices like our brain chip and Pixhawk. The Pixhawk is our flight controller. It's on the bottom. It interfaces with the sensors and controls the motors. We're building the UGV as a all-terrain vehicle using tank treads and 12-volt motors. We're using Raspberry Pi, Pixhawk, and Here 4 as the sensors and computational power. On the Pi, we're using the brain chip to implement a kill switch using word detection. We're using a Arduino to translate the pulse width modulated signal from the Pixhawk to the motor driver, and we're using a large metal sheet as a landing pad that will be mounted on the UGV.
Our software stack consists of ArduPilot, the flight controller firmware, the DroneKit Python API for communicating with the firmware, as well as ROS2 for publishing and retrieving sensor data from our autonomous vehicles for our mission logic scripts. Before hardware integration, we made sure to test our mission logic in the Gazebo simulation software, as well as with the ArduPilot shuttle vehicle software. This allows us to test without risk to the physical components of the autonomous vehicles, as well as the safety of the drone pilot. Our non-GPS based navigation method is facilitated by the lightweight visual inertial algorithm OpenVINs. With ROS2, we can deliver the input from our camera and IMU to OpenVINs and return its odometry estimates to ArduPilot in replacement of GPS for navigation and stabilization during flight. Object detection for obstacle avoidance is achieved with the YOLO V11 algorithm, which is optimized for devices like the Pi 5 and provides accurate detection performance, thus being a great option for our use case. Additionally, the UAV and UGV collaboration cannot be facilitated with a ground station. Therefore, we decided to implement Bluetooth for our vehicle-to-vehicle communication method. Bluetooth is a great option for outdoor environments, thus being a good fit for our use case.
Our lessons learned include provisioning more powerful computer hardware equipment for software and simulation testing. We ran into the issues with performance in the simulated environments due to the lack of memory and the experiment being too computationally expensive. We learned to use the best tools available to help choose the hardware components and to test each component before integrating it. We experienced difficulties navigating the parameters in ArduPilot firmware, leading to issues relaying information from the Here 4 to the Pixhawk. As a team, we've grown so much from this project and are excited to show what we've accomplished at the competition. Thank you.